Hello everyone, this is Bhupesh Kumar. First, I will thank the organizer of the conference who invites me to this conference to present my work. Right now, I am working as a postdoctoral researcher at the University of St Andrews, Scotland. I am going to present the work I did in my previous postdoc at Bar-Ilan University, Israel in the group of Professor Patrick Seba. I'll talk about controlling random lasers to investigate localization. Outline of my talk is I will start with brief introduction to random laser, why laser control is required, and I'll talk about various methods used to control lasers, and we'll talk about the method we use to control random laser emission in presence of strong mode overlap. I'll show single mode imaging of localized lasing modes in random laser, slope efficiency enhancement of single lasing mode after selective pumping, optimal outcouple modes in random laser, strong interaction between localized lasing modes of a random laser, and impact of nonlinearity on localization. Conventional laser use mirror to reflect and amplify light in a laser cavity, also known as resonator. Light consists of two mirrors placed at opposite ends, with one mirror being partially transparent to allow small amount of light to escape as the laser beam. When external energy source such as electrical current or light is applied to the gain medium in the cavity, it excites the atoms or molecule within the laser medium, cause them to emit photons of light. These photons bounce back and forth between the mirrors and coherent light is emitted through the partially transparent mirrors. Random laser is an active medium with lots of scatterers. In random laser, multiple scattering of light by scatterer increase the time spent in the gain medium and provide the necessary feedback for amplification and lasing. Random laser is therefore can also be called a mirrorless laser. Lasing is expected in such a medium when gain overcomes the losses. Since the gain is proportional to active volume, the losses result from leakage out the surface of this volume. There must be a critical volume where the threshold is reached. Such type of lasing is also known as incoherent random lasing. There is in such random lasers, resulting emission is a broad spectrum of incoherent light with no well-defined directionality or coherence. The bottom figure shows typical spectrum of incoherent random laser. Beyond amplified spontaneous emission that result from increased dwell time, is lasing with resonant feedback is possible in such a mirror. But the experience which really triggered the random laser story was carried out by Huika group at Northwestern University in 1999. They pumped zinc oxide semiconductor powder and observed first narrowing of the gain curve, followed by the appearance of sub-nanometric lines in the spectrum as shown in this image in the center, analogous to real lasing modes of a conventional laser. These narrow line width lasing peaks confirms that scattered light inside the gain medium is trapped in a closed loop and interfere constructively to show coherence properties, unlike non-resonant random laser. After that, random lasing is observed in different type of disorder systems in different wavelength bands. Bottom left, a micro-random laser by the same group. Such micro-random lasing devices can be an interesting solution to overcome the difficulty to produce highly reflective mirrors to trap light at small length scales. 2D experiment again in zinc oxide powder. Zinc oxide powder is favorite because it emits in the UV range where it is very difficult to make mirrors. In this context, mirrorless random lasers are alternative for lasers at those wavelengths. Random lasing in opals and photonic lasing glass infiltrated with dyes has been observed, and random lasing in cold atom gas by Kessler group, optofluidic random laser by Patrick Seba group, and after that random lasing in photonic crystal with intrinsic disorder. Random laser emission is a multi-wavelength emission without any directional and spectral control. Therefore, to make random laser suitable for any practical application, it is important to achieve emission and directional control. There are other benefits of benefits of having a laser control, which are laser stability, and that to enhance power output and stability for a given pump power, optimize the pump profile to reduce the lasing threshold. How we can achieve laser control? There are various methods to do that. By designing a suitable gain medium, optimize the optical cavity or photonic structure, shape of the microresonator such as spiral shape or optimized, designed in photonic crystal nanocavity. Axion lens is used for bringing the pump beam into coincidence with the whispering gallery modes confined near the outer rim of the cavity to achieve to achieve maximum optimal output of a laser, tailoring the gain distribution by selective pumping, finding an ideal spatial profile that overlaps strongly with the optimally outcoupled mode to control various lasing characteristics including emission directionality, threshold, and lasing frequencies. To control over random laser, which I will explain in the coming slides, we choose the method of spatial modulation of pump profile. This method of selective pumping can be used to control laser emission wavelength and directionality and reducing the lasing threshold. This pump shaping method has been successfully applied to microresonator to extract optimally outcoupled lasing mode, asymmetric resonant cavity, and spectral selection in optofluidic random lasers. We have designed a solid-state organic random laser which benefits from laser stability, sample longevity, and most importantly for our study, relatively strong scattering, a necessary condition to observe the regime of Anderson localized in a finite size sample. To fabricate our laser, we prepare a 600 nanometer thick layer of DCM dye doped polymer spin coated on a fused silica plate. This layer is structured by engraving hundreds of parallel randomly spaced air grooves using E-beam lithography. The control disorder is introduced by varying the groove position around 8 micron periodic arrangement. A small section of the sample with air groove is shown by some images. When this sample is optically pumped, the scattering is provided for random lasing. Scattering is provided by 125 parallel air grooves which are randomly distributed along a 1 millimeter long sample with an average spacing of 8 micrometer. Air grooves provides an index contrast of 0.55 with respect to the PMMA layer, which helps in strong scattering and localization of light. Here I will briefly talk about Anderson localization, which is in a sufficiently strong scattering media, light transport is suppressed and modes are exponentially localized. This phenomena is called Anderson localization. It was first predicted in 1958 by an American physicist, P.W. Anderson, so it is also named after him. Anderson localization is a general wave phenomena that applies to the transport of electromagnetic waves, acoustic wave, quantum waves, spin waves. It has since been observed in various systems like non-interacting Bose-Einstein states, localization of ultrasound waves in 3D elastic network, transverse localization of 2D photonics by Motisage group, localization in matter wave. Here is the schematic of our experiment setup where we use 532 nanometer beam of a frequency doubled mode lock ND-arc laser, which is first expanded on a computer-driven spatial light modulator which offers the possibility to modulate spatially the pump intensity. The reflected laser pattern from the SLM is demagnified further and imaged on the back of the sample. A fixed stage optical microscope magnifies 10 times the field intensity scattered at the surface of the sample on the camera. A laser strip of length 500 micrometer and width 50 micrometer from a frequency doubled ND-arc laser is used to pump uniformly the random structure. At laser energy above threshold, multiple scattering provide the necessary optical feedback to reach laser oscillation. At sharp decrease, discrete peaks appear on the broad spontaneous emission background. As it is most often the case with random laser, emission is multimode. We also uh, image the out-of-plane laser radiation under a 10 microscope objective. Top figure shows out-of-plane scattered light at the position of air grooves. In contrast, the image below it shows uniformly distributed spontaneous emission detected when the sample is pumped below threshold. The field intensity distribution due to the uniform pumping inside the sample is recovered after subtracting the SE spontaneous emission distribution shown in bottom right. We will use iterative pump shaping method for spectral control of our quasi-1D solid-state random laser. This is an iterative optimization method based on spectral feedback. The pump intensity profile is tailored based on the recorded spectral feedback until the target mode is selected and other lasing modes are suppressed below the threshold. To achieve single mode operation at a desired wavelength or target wavelength, we need to find the pump profile which maximizes the intensity ratio of the target mode and mode with intensity count next to the target mode. To design our specially modulated pump profile, we choose 32 Coulomb vector of the 32 by 32 binary Hadamard matrix as the initial vertices to initiate the optimization procedure. We choose Hadamard basis as all the element of it has the same mean amplitude, and we perform optimization using Nelder-Med simplex method. Our 1D pump profile is made up of 32 intensity lines, and each line can be grayscale coded on 256 levels. Figure A shows multi-mode lasing spectrum of our random laser. So we first aim at selecting a mode, individually selecting a mode that is not the first mode to laze under uniform pumping. So we choose lasing mode at 599.80 nanometer, and after running 200 iterations, a non-uniform pump profile is found, shown in top of figure I, which optimally select the target mode at wavelength 599.80 nanometer and reject all other lasing modes to below threshold as shown in figure B. Remarkably, pure single mode operation is achieved here. The out-of-plane scattered light imaged from the top of the sample corresponds to the intensity profile of this lasing mode, which is shown in figure I. This lasing mode is found to be spatially confined away from the sample limits, and that indicates that random lasing indeed occurs in localized region. The same operation is reproduced to select other lasing mode from the multimode emission spectrum in figure A. For each mode, new pump profile is systematically found that select all these modes. Imaging these selected modes show that all these modes are spatially localized. Figure B to G shows emission spectrum of 6 individually selected lasing modes and their corresponding lasing mode intensity distribution or field distribution together with their optimized profile is shown in figure 1 to I to N. Here I will demonstrate the experimental estimation of the localization length of our sample. Lasing modes are found to be exponentially localized in different regions of the sample and occupy a significant fraction of the sample length, as I have shown in my previous slide. Despite strong spatial overlap, it is possible to measure their spatial extension. The easy access to intensity distribution of individual localized mode allow us to explore the probability distribution of their localization length. Its inverse, which is Lyapunov exponent, is expected to follow a normal distribution in a sufficiently long 1D random system with weak disorder. That is the case in our sample. So here we measure the mode extension of 75 modes individually selected in 10 different samples with different disorder configuration. All the samples are carefully manufactured under identical conditions. We define the mode length as the distance between the extreme scattering groove from which intensity of the light scattered is above the noise level. The inverse mode length probability distribution is plotted in the figure together with the normal fit shown by the red line. A tail to the distribution indicate a departure from the normal distribution. Half of the mean value of the distribution gives the average localization length, which comes out to be 100 micron in our case. Inset in this figure shows intensity profile of a localized mode in log scale, which gives the signature of Anderson localization in our 1D sample. Now I will show slope efficiency enhancement and reduction in lasing threshold by selective pumping of localized modes. I point out that the optimization algorithm does not trivially converge to a narrow pump profile near the center of the mode, which would have been sufficient to select specially isolated and strongly confined modes. Here, the distribution of the pump intensity extends far beyond the center of the modes. The reason for this non-trivial optimal pump profile is that modes overlap significantly in our system, and therefore these modes compete for the gain. Optimal selection of a single lasing mode necessitates, therefore, to disentangle the interacting lasing modes. This is achieved by suppressing the whole burning effect and turn off the mode cross saturation. The ability of pump shaping to isolate each mode individually is demonstrated in this figure, which compares lasing characteristic of a mode lasing at 599.78 nanometer for a uniform pump shown by a blue plot and optimized pump profile shown by the red plot. When the system is pumped uniformly in multi-mode regime, the targeted mode emission at 599.78 saturates rapidly, impeded by mode competition and cross-saturation between different lasing modes. Once optimized, this same mode, the lasing intensity of this same mode becomes linear with pump energy, and confirming that there are no other lasing modes simultaneously because there is no mode competition. The selecting profile is found to be efficient in preventing the spatial hole burning below and far above the pump energy at which optimization is performed. Strikingly, the threshold of the lasing mode after optimization is reduced by a factor of 1.5, while the slope efficiency of its laser characteristics is increased by a factor of 6 when compared to the same mode lasing in a multi-mode regime under uniform pumping. That means the energy coupled out of the random laser is more efficiently for this particular mode when it is optimized or when it is optimally pumped. So this selective method used here release the selected mode from competition for gain with other modes. Individual imaging of localized modes allow us to investigate the impact of nonlinear gain and gain saturation on a single localized mode by increasing the pump energy and monitoring the mode profile. We first select a mode lasing at 603.10 nanometer, and this mode is localized near the center of the sample. We check that this mode is preserved under local pumping, and subsequently we reduce the pump size to a small 10 micrometer long pump strip applied which near the mode center, sufficiently enough to excite this mode. So here we prefer a focused local pump over an fully optimized pump profile to increase the energy density and make sure the gain saturation can be reached without sample damage. The pump energy is increased stepwise from threshold level, which is 14 nanojoule, to saturation level 147 nanojoule and beyond that up to 200 nanojoule as shown by plot on the right side. The lasing mode profile is recorded at different pump energy level as shown in the left figure and their corresponding bar plots also shown in the middle. We observe that mode profile is perfectly preserved although its peak intensity is increased by 3 order of magnitude and dye saturation is reached. So this is a clear and direct evidence that localized modes are insensitive to nonlinear gain even in the presence of gain saturation. Interaction-induced mode switching in random laser. In this experiment, lasing mode at 606.33 nanometer is individually selected with and its optimized pump profile is shown in figure A, top left. We split this pump profile in two equal parts. When we pump only left half and turn off the right half, the lasing mode at 606.33 turn off and new lasing mode at wavelength 620 nanometer start lasing. Now we monitor the emission spectrum while gradually increasing the intensity of the half of the pump profile which we initially turn off. Starting from single mode spectrum at 620 nanometer, we observe that intensity of this mode starts decreasing and new lasing mode at a wavelength 606.20 start coming out above the threshold. Eventually, lasing mode at 620 nanometer is switched off at higher as we apply more pump to the half of the pump. So this process is totally reversible. And figure D here shows the log plot of the peak intensity of the two modes during interaction. The onset of the new lasing modes at the expense of other lasing mode can be explained in terms of cross gain saturation. The strong competition for gain increase with spatial overlap of the two modes. By imaging individually the intensity profile of these two lasing modes, we confirm that these two modes are highly spatially overlapped. To summarize this work, we have demonstrated that single mode random lasing with high side lobe rejection can be achieved by using iterative optimization of the optical pump profile. We show that spectral control and near field imaging can be used to investigate localized modes in a random laser, and optimal pumping of localized lasing mode leads to reduced lasing threshold and enhanced slope efficiency. And we have also achieved mode switching in our random laser, and we have also shown that the individual localized modes remain highly unaffected by gain nonlinearities. Thank you. If you have any question, please feel free to contact me in the given email address here.